Good morning, students. Am I audible to you? None for
Yes,
this.
sir.
Okay, all right. Thank you. So let us recall that we have briefly introduced the idea of duality. So duality is actually related to the optimization problem for which a given problem can be seen as another optimization problem for which the objective will be distinct. The same problem can be treated as a minimization problem, or if we say change the situation, the graph will be same. Let us change the situation. If I change the situation, then it can be treated as a maximization problem. So that was in the last class we have seen. And then we have seen that for a given LPP, for a given linear programming problem, we have found another linear programming problem by some multiplications and additions. So for example, we have multiplied with A1, A2 and A3, and then we have seen that this is actually giving us uh, the upper bound of the objective function. So we will try to go down to find out the optimal solution, because for this problem I think optimal solution will be 36 or something, but by this rough calculation we can get up to 45. So we are getting a rough idea that this is actually less than 45, less or equals to 45. So the maximization value cannot exceed 45. So this will give us one kind of brief idea or rough idea. Okay. Now we have seen that if we multiply with A1, then the problem is actually becoming in this form. In the last class we have seen. Okay. So another LPP. Now from now onwards, what we will call this is as primal problem. The given problem will be called as primal LPP, and the problem that we are actually obtaining from this one, so it will be called as dual LPP. Okay. Now some of the observations you can note. Okay. What are those observations? Observations is that here number of variables is 2. In this problem, variables are 2. Constraints are 3. Okay. So variable number is 2, x1 and x2, and their number of equations, number of variable is here 3, a1, a2, a3, and then constraint is here 2. So these are some changes that we can see. That, and also the coefficient matrix for this primal problem is this one. A is equals to 1, 2, and 1, and then 5, 3, and 1. So 5, 3, 1. Okay. Okay, fine. Then the coefficient matrix for this dual problem, we can see it is just the transpose of A. So if we transpose it, so it is getting A transpose and it is giving the coefficient matrix. Not only that, we say that the cost matrix, this is C1, this is C2, the cost matrix are now actually the variables B1 and B2, the resource. And these resources 18 is actually coming here, 15 here, so say 7 here. Okay, so in this way we can just find the relationship between the primal problem and the dual problem. Okay. Now we have seen that the problem is actually if you try to actually relate these two things. So this black this bar can be treated as the primal problem. Primal problem, while these greens are actually the objective value of the dual problem. Okay. For example, if you remember the problem that we have discussed, maximize 8x1 plus 6x2 subject to x1 plus x2 less equals to 5, then 3x1 plus 2x2 less equals to 12, where x1 and x2 greater equals to 0. So if you multiply this one, the first constraint by, if you multiply this first constraint, for example, if you to find out the upper bound, we want to find out the upper bounds. Is upper bound? As you know that infinity is always z equals to infinity is a upper bound. Is an upper bound. Then if you multiply this one with 8, then you can see that z equals to this 8x1 plus 8x2 less equals to 40. So this is greater than equals to 8x1 plus 6x2. Yeah. So this is this relation is valid because this x1 and x2 are greater than equals to 0, and we are multiplying a positive number. We can also, if you put 0 here and some quantity some 3 here, then also it is possible. Okay. For example, so this is z equals to 40 is an upper bound. Now can we remove, I mean, can we reduce something more? Because we know that for maximization problem we have seen that optimal value is 34. Z max is 34. So if you multiply by this 3 and this one with 0 and add them, so what will happen? So this will give you 9x1 plus 6x2 less equals to 36, and this is less than equals to 8x1 plus 6x2. So z equals to 36 is also an upper bound. That means we are able to reduce the gap between the expectation and the original solution. Original solution is 34, original objective value is 34. We have come. Now can we further reduce? From there we can reduce 34. I think we can select some suitable coefficients, suitable integers that we can multiply. For example, if we multiply this one with 2, not 2, 2 and 2. So this will become 2, 2x1 plus 2 to 6, 6x1. So 2 plus 2, sorry, 2 plus 6 into x1 plus here 2 plus 4. So 2 plus 4 x2. Okay, and the right hand side will be this is 10, 5 into 2, 10, 12 into 2, that is 24. So 10, 30, 24 plus. So we are actually able to find out that 34 is an upper bound. Okay, we can see that this is exactly what is given 8x1 plus 6x2. This is bounded by 34. We can see that without solving without using the simplex algorithm, we can find the upper bound that the maximum value of this objective function cannot exceed 34. So in this way, what we are going actually, we are going down. But in the simplex algorithm, we have seen we start with 0 solution, z equals to 0. Then we have, in the first iteration we have got 32. In the third iteration we have got 34. So that is also, if you go top to down, then the value is increasing, objective value is increasing. Okay, but if you go from top to down, the value will be decreasing. So finding the minimum of those upper bounds is actually will equate finding the maximum of these objective values. Okay. This is actually calculating the lower bounds actually. You can say they are lower bounds. So this value will be at most, will be at least this much. So when this maximum value and this minimum value actually coincide, then we call it a optimal solution. So for that optimal stage, this the minimum value, the minimum, the objective function of this problem, the primal problem, and the objective function of this dual problem will actually coincide. But remember, this is only true for linear case. If it is non-linear problem, then this relation do not hold. Yeah, this does not hold for the non-linear problem. So that is why I have taken one strip. So if you think about so finding the minimum of this, if you think about the green is the dual. So among this, all these, if you find the minimum value, it is here. And for this black strips, if you find, so this is actually primal values. So if you try to find out the maximum, so maximum here. So this is a nice, graphical representation of primal and dual objective functions. Okay. Now let us summarize in a compact way. So that generalized form is this one. For a primal problem, maximize Cx, and then the constraints are given in this way, then xij equals to 0. So we have already seen that number of variables, we have to first decide how many variables are there. So number of variables is 2 here. So 2 will be the actually number of constraints. Okay. And here equation 1, 2 in constraint 3. So 3 number of equations, number of constraints. So the number of variables will be 3. Okay. And also we have seen that Cj are actually now the resource constraints. And then Bi are actually now the cost of this form. Okay. And of course, both we will talk about Yj, Xj and Yi are greater or equals to 0. We will take only for non-negative values. Okay. That is one statement. Now, if you just try to look back, and then here we had all the constraints as less than type. Okay. And this was a maximization problem. So the objective was maximization. The objective here will be minimization. And the constraints are less than type. Now we can see here constraints are greater than type. Now what will happen if we have a equality type or greater than type? What will be the corresponding uh, the inequality or the equality of the variable? I mean in the dual problem, that we have to discuss. So for that there is a small concrete table actually. So for which we will actually talk about. Okay. Yeah. So if the problem is a maximization, primal is a maximization, and it has of this form. Okay. Primal, even if the primal some greater than type or equality type is constraints are given, we can make them of this form, right? So if it is the primal problem of this form, then the dual will be of this form. We'll try to keep this, I mean, to make that convenient that it will follow only one type of inequalities, either less than type or greater than type. Okay. Okay, right. So this relation is actually telling the relationship between the primal and the dual problem. The first table, first summary, this one tells relationship between the problem, primal and the dual problem. If the primal is a maximization, then the dual will be minimization. If the minimization primal is minimization, then the dual will be maximization. Number of variables will be the number of constraints of the dual. Number of constraints of the primal will be the number of variables of the dual. So right hand side vector of the primal will be the cost vector, objective function coefficients will be the dual, and the objective function values, the cost vectors will be the right hand side values of the dual. And the constraints coefficient, if it is A, the A matrix, then the constraint of the coefficients will be A transpose. Okay. Now this second summary, this says primal dual relationship between the constraints and the variables. So if we have less than type constraint, then the variable will be greater than type. If the constraint is less than greater than type, then the variable will be less than type. So it will be reverse type, because the constraint number of constraint is actually associated with the number of variables, and the number of variables is associated with the number of constraints. So that is why constraint and variable. Here is constraint, it is variable, but it is less than type, the variable will be greater than type. Here it is greater than type, the variable will be less than type. Now if we have equality constraint in equation, if we have equation, then the corresponding variable will be unrestricted variable. That is a free variable. Now if we talk about the variable is greater than type, then the constant, the corresponding constant will be greater than type. And then if the variable is less than type, then the constant will be less than type. If the variable is unrestricted, then the corresponding equation will be, the corresponding constant will be an equation. So with this information, we will try to look at some examples. Now we can say that this is a minimization problem. So for minimization problem, we will try to keep it as greater than type. Now we can see that this is constraint number 1, constraint number 2, constraint number 3, constraint number 4. This is constraint number 5. But we can see that there is a discrepancy. There is a odd, this is odd in this setup. This is a minimization problem, but this is less than type. So we want it a greater than type. So what we will do? We will multiply by -1, and then we will rewrite. So minimize 3x1, minimize z equals to 3x1 minus 2x2 plus 4x3, and then subject to this is 3x1 plus 5x2 plus 4x3 greater than equals to 7. Then 6x1 plus, the problem will be rewritten, and x2 plus 3x3 greater equals to 4. We will multiply by -1. Okay, so this is minus 7x1 plus 2x2 plus x3 greater equals to -10, and then x1 minus 2x1, sorry, 2x2 plus 5x3 greater equals to 3. So and the next step is to write the last constraint for x1 plus 7x2 minus 2x3 greater equals to 2. Now we have 5 constraints and 3 variables. So let us just fix for primal. If this is a primal, okay, first task is number of variables is 2. No, number of variables is 3 here, and number of constraints is 5. So the dual will have number of variables will be 5, and the number of constraints will be 3. So we have to decide what we can do. So let us write of this form. So the problem will be like, we call for this constraint, let us write y1 is the corresponding, so y2 is the corresponding variable, y3 is the corresponding variable, y4, and then y5 is the corresponding variable. So what will be that? This is a minimization problem. So the problem will be maximize. Remember, these resource vectors are now will be put into this form. So maximize. Okay, let me write down. Maximize W. Let us call W as the dual objective. So 7y1 plus 4 y2 plus, sorry, not plus, it would be minus, because we have written it in this form, minus 7x1 plus 2x2 plus x3 greater equals to, so this is minus 10. Okay, so this would be minus 10 y3. Then we can say it plus y4 will be there, so 3y4 and plus 2y5, and the subject to constraints are now, okay, so this is actually changed now. So let me just rewrite it. Okay, the third constraint is this one now. Okay, so for this one we will write y3. Okay, now what will happen, that y1, because we have written all the variables, all the constraint in terms of greater than type, so we can easily follow this, we can easily apply these relations. Okay, okay, right. So this is the variable, so 3x1 3y1 plus 6x2, sorry, 6y2, y3 is here, so minus 7 y3, and then here plus 1 into y4, so y4, then plus 4 into y5, 4 y5. Okay, since that, so let us write, the right hand side will be 3. Okay. And because we want y1, y2 and y3 greater or equals to 0, so we have to wait whether this will be greater than or less than. So this is actually, so first constraint is less than type. Okay, okay, for dual, for minimization, so for example, the variable is less than type, so the constraint will be constraint is less than type, constraint is greater than type, so the variable will be less than type. Okay, the variable is actually here greater than type, and the variable is also greater than type, sorry, greater than type, so the constant will be greater than type. Yeah, so all the variables we can see here, all are greater than type, so the constant will be all greater than type. We cannot say about this now. Okay, so greater than type we have written. So the second constant will be 5 into 5y1 plus 2y2 minus, not minus, this is plus again, plus 2y3, then it is minus minus 2y4, then plus 7y5. Since x2 is greater than type, so the second constant will also be greater than type. So this is, but this value will be minus 2, right? So we'll have to write here. Okay. So this will be minus 2. The coefficient will be minus 2. Okay. Now the resource is minus 2. And then the third constraint that we have is 4y1 plus 3 into y2 plus, here it is, 1 into y3. So this is y3 plus this one. This is plus 5 into y4. And then we have minus 2 into y5. Then third variable is greater than. So let us write the third constraint as greater than is not greater than 0. The third variable is 4. Okay. So constraints are actually okay now. How about variables? So if the variables are actually greater than type, then we have to, okay, if the constraints are greater than type, then y4 and y5 all has to be greater than. So this is a minimization problem, and actually the relation that I have said, actually for here, constraints will be actually greater than type, greater or equals to 0. I will tell you the confusion, how it is, where it is happening. Because this table is actually given based on the primal as maximization. This primal is given as a maximization problem. But in our case, the primal is actually given in the minimization format already. So what we have to do actually, so we are supposed to do, we make it a maximization problem. We write it as maximization, and this criteria should be converted into less than type, and then we apply, and there will be so many substitution actually will be there. Okay, but since we know these relations, okay, once we know these relations, we can directly go to the solution. Yeah. If this is the minimization type, for primal is a minimization, okay, and dual is a maximization, then this relations will actually change. These conditions will change. For that, actually, we have to see some more examples. Okay, so this second problem is over now. Okay. Oh, sorry, I have made mistake. This is actually supposed to be maximum. For maximization problem, we have to, yeah, we are supposed to get less than type, but I have written some wrong actually. Okay, let me just clarify again. If we do that, if we do some mistake, so let us not do in this way. Okay. So in order to make this, in order to avoid this confusion, I will actually have to rewrite again. So if we just try to make it as a, let us write it as a maximization problem. Maximize z minus z minus 3x1 plus 2x2 minus 4x3. Then we'll try to make it in this other form. Okay, subject to 3x1. So we'll all the equations we'll try to write in the negative form. Minus 3x1 minus 5x2 minus 4x3 less equals to minus 7. Then we'll try to make it minus 6x1 minus x2 minus 3x3 less equals to minus 4. It is already there 7x1 2x2 minus x3 less equals to 10. So it is given. Then x1 minus 2x2 plus 5x3 less equals to minus 3. Then we have to minus, so minus 1 plus 1 minus 1. Okay. And then finally minus 4x1 minus 7x2 then plus 2x3 less than equals to minus 2. Okay. Now again we have to write the actually dual problem. Now we have put it into a standard form. Okay. So for this, what we'll write? So the problem will become now minimize w. So this is minus 7x1, sorry, y1 plus, not plus, it would be again minus 4 y2 then plus 10 y3 minus 3 y4 and then minus 2 y5 subject to the constraints. The constraints, there will be 3 constraints so far. That is minus 3x1 minus 6x2, sorry, not x. Now we have 12 variables are y1 minus 6 y2 plus 7 y3 then minus y4 minus 4 into y5. Since these are greater than 0, so this variable will also be greater than. The coefficients are 3 here, so let us write 3. Then minus 5x y1 then and then minus, here it is minus 1 minus y2. So this is minus already minus y3. This is plus, so plus y4. This is minus, so it will become minus. Let me just write minus 7 y5 greater equals to, so x2 is greater than, so second constant will be greater than, and the coefficient is minus 2 here, minus 2. Okay. Then so minus 4 y1 then minus 4 y1 and this is minus 3 y2. This is minus y3. Okay, right, minus y3 and then 5 minus 5 y4. Then this is plus, so plus 2 y5. The third variable is greater than, so this greater than equals to, okay, right now. So These coefficients are now changed. Sorry. Okay. We have to think about this one. I am thinking about this one. So this is not correct. So this is actually -3. And this is greater than +2. And this will be greater than -4. And y1, y2, y3, y4, y5 all are greater or equals to 0 because the conditions that we have seen, the constraints are less than type, so variables are greater than type. Okay. Now you can actually make it. If you write it another way, so write maximize w, maximize -w. So this will become 7y1 plus 4y2 minus 10y3 plus 3y4 and then plus 2y5. If you just maximize it, so this will become subject to the constraints. So let us write. Let us so since this is maximization, we want them into less than type. Okay, so this problem. If you multiply with -1, so this will become 3y1, then 6 plus 6y2 minus 7y3 plus 4 not 4 y4 and then plus 4y5. This is less than equals to 3. Multiplying with -1. So the second constant will become -1 again if you multiply. So this will become so 5y1 plus y2 plus y3 minus y4 plus 7y5. The right hand side is +2, so this will become -2 because the problem is in this maximized form. Okay, so we have to write it in this proper format, and then so this is 4y1 plus 3y2 plus y3 plus 5y4 then plus 2y5, sorry, not plus, it will be minus, and then less than 4. Okay. And all are actually y1, y2, y3, y4 and y5 are greater or equals to 0. So that will be our final answer actually. So given primal is given in this form. So this will be the dual. Now the only change we can see here, because this constraint, the third constraint, in the second constraint we can see, and this is due to since we have one, the right hand side is becoming negative because we have one different type of constraint in this format. So this is what actually is written in this form. Okay, right. So similar type of examples are given here. So if we have equality type, then what will happen? So this can be written as x1 minus x2 is greater than equals to 30, and x1 minus x2 is less than equals to 30. And then since this is minimization, so we'll make everything as a maximization greater than type constants. So this is, we have to make it greater than minus 1, we have to multiply, and this one we again minus 1 we multiply, and there will be the constants will be in this form. So for this purpose we have written all the constants are written as greater than type. So this is greater than, now we are getting one less than type, so this is, we make it greater than type. Okay, all the constants are now greater than type. Okay, so we'll rewrite it. Okay, and then we can see that there is a unrestricted variable. So for unrestricted variable, we will see what will happen. So since this is a 4 variables, number of variables, sorry, number of constraints are 4. So variables will be initially 4, and the number of constraints are 4. So number of variables are 4. And number of variables is x1 and x2. So the number of constraint in this case will be x1 and 2 will be there. So once we write all the variables, we can see that this is a common y2 minus y3. We can take it common. So for that we can substitute y. Okay, as we can write it as an unrestricted variable. So y2 y is an unrestricted variable. So this is coming because we have one equality constraint. Okay. So same type of examples are actually there. So you can just look at these problems, and then this is a very important. Here everything is considered: equality, then greater than type, less than type, again greater than type. Finally, x1 is greater than type, x2 is unrestricted, and x3 is less than type. So what will be the dual of this problem? And also this is as given as minimization problem. Okay. So the first task will be to make it as a maximization. Okay. So this minimization problem is written as maximization. Okay, right. We have written this as a maximization problem, and all this criteria, there is a constraints are there. We have written it as a one is greater than type, greater than 12, another will be less than 12. So whatever may be the case, we'll write is a less than type criteria. So this is less than, less than. We have made everything as in terms of less than. So make it less than type, rewrite it, and then shift it. So make it the changes. Now we have to make, we have to think about the variables also. This is unconstrained. This is less than type. So for less than type criteria, since it is less than, we will make it as greater than by substituting some different. Yeah, this is unrestricted. So we'll put as a difference of two variables. And since this is x3 is less than, so we'll put x3 equals to minus x6. Okay. Since x3 is less than type, so this will become greater than type. X6 will become greater than type. So everything is satisfied now. Okay. So we'll put everything here, put on here, substitute there, and then we'll simplify. From here, you go to there, and then here, after here. So the final actually output, the given problem, and this is the final problem. Okay. So these are some exercise. Yeah, try to find the verify. Try to find the dual of this problem. give you only one, because it is also having less than, greater than, and equality. So try to follow the steps that is given in the previous step, previous problem. So I will stop here today. In the next class, we will discuss some more on this topic, the duality of a LLPP problem. If you have any doubt, you can ask me.